Okay, welcome everyone to our ZAC seminar. Today is my big pleasure to introduce Mara Ungureanu, who was an undergraduate student in University of Edinburgh. I taught her a long time ago, and then Mara did PhD in Berlin, and now she's a postdoc in Freiburg. And Mara will speak about counts of seconds, planes to varieties, the generations, and universal polynomials.
Yes, so thank you, Vanya, very much for the introduction and for the invitation, and hello to all of you in the audience. So as you might guess from the title, the aim of this talk today is to explain to you a few things about the enumerative geometry of secant varieties and to show you the kind of the flavor of the tools, of the kind of tools that one uses in this kind of study. The plan is as follows. I would like to begin with a small background and motivation as to why actually we are interested in studying these secant varieties. And then once we do that, I would actually like to restrict to just secant varieties to curves. And you might think that this is quite a big restriction because, okay, curves just one-dimensional, but actually the subject is still very rich and there's still many questions and many beautiful problems that you can ask. And in particular, the kinds of problems that I'm mostly interested in so far have been of the kind of enumerative geometry and dimension theory kind of questions. And this kind of leads us into two distinct directions, if you want. And these two distinct directions are in this part 3 and 4 here. So on one hand, in order to understand, for example, whether the counts that you're doing using intersection theory are correct or valid or whatnot, then you really need to understand the geometry of, say, the secant variety that parameterizes some secant planes. And so these degenerations, so the generations to nodal curves, are very good tools to help you understand the geometry of a secant variety. So this kind of fits in sort of the verification part of the endeavor. But then, of course, you also need to compute some numbers. And to compute these numbers, okay, you have various tools in intersection theory that you can use, all sorts of computation methods for cohomology or classes and so on. And I hope, if time permits, I would like to tell you about some tools that I hope are going to make some of these computations easier. So this kind of fits into the calculation side of the endeavor. Okay, so let's begin. So the first question is, of course, why should we bother to study secant varieties? And one possible answer is that the secant varieties are everywhere. So for example, you just have applications to just pure algebraic geometry. For example, if you want to understand if some varieties have projections to some projective space of a fixed dimension, then you end up asking some questions about secant varieties, but you also have more applied applications if you want. So for example, they show up in algebraic statistics. There you have some statistical model and you have a dictionary that translates statistical models into certain kinds of algebraic geometry objects. And in this case, you have some special kinds of models called mixture models that correspond under this dictionary to secant varieties, and they appear in the study of phylogenetics and so on. They also appear in signal processing, so that's also very cool. For example, when you do signal processing, you might be given a tensor and you might have to decompose it in tensors of smaller rank, and then again, you can reformulate this question in terms of writing down the equations of secant varieties. Very good. So this is kind of why we care, but of course I still haven't really defined or said precisely what they are. So let me do this now. So I want to say that I think that the first encounter an algebraic geometer would have with the secant variety kind of goes as follows. I have a variety in some projective space that is not contained in a hyperplane. And now I'm going to define the ETH secant variety of X. in the following way. So this I'm going to denote by v of x, and I'm going to define it like this. So I'm going to take E points in general position, P1 up to PE, and I'm going to consider the E minus 1 plane that this guy is defined. So this E minus 1 plane, what I mean by that is that this is a projective space of dimension -1. And I'm going to actually consider all of these guys that I can possibly think about on my variety, and I'm going to take, there's a risky closure of it. And these are, it's important, these are in general position. So of course, for example, if E is equal to 2, this is the variety that parameterizes all the lines that go through your variety of choice. And we know quite a few things about this. And of course, you can this is just like a set theoretic description. You can put the structure of a variety on it quite easily. And for example, we know quite a few things if this variety that I have is a rational normal curve. So the fact that this rational normal curve is quite rigid, so in some sense all the points on it are kind of as independent as possible, you expect that this might have some good effect on the study of the secant varieties to it, and that's true. For example, it's quite easy, or rather, okay, not super hard to see that the degree of the secant variety in this case is given by r minus e plus 1, choose e. And okay, you have to be a bit careful in this case, have some condition to make things work nicely. So, okay, this is a happy case because, of course, the rational normal curve is a very special kind of variety. But in general, and especially for higher dimensional varieties, these kinds of questions, even what the degree of the secant variety is, are quite complicated. And not just the degree, but also maybe the defining equations, syzygies, and so on. These are things that are actually really hard to consider. And so we are trying to, you take things one step at a time. So, okay, let's consider now from now on just curves, and not necessarily rational normal curves, but any curves that we can think about. So I'm going to specialize now to secant varieties on curves. And I'm going to actually consider not just the secant variety that I defined just now, but also a more refined version of it. And the refined version of it means that I'm looking also at special secant planes. So what that means, these special secant planes, what I mean by that, they are basically subspaces that meet my curve C to meet the curve C in a dependent set of points. So this is just slightly rephrasing what we have said just now in order to be able to refine it a bit. So for example, if you look here in the pictures that I have a curve C here, and I have a line that intersects my curve in 3 points. So that is a 3 secant line. Or I have another curve and another line that intersects it in 4 points, right? So these are points that are dependent, but they actually lie on a line, not right? So these are slightly bit different from what I said from the first definition that I gave. But of course, now I would like to make that a bit more precise. And so I'm going to do that by saying that, okay, actually the question that you're going to ask yourself in this kind of context is when to expect, say, a curve C in PR to contain E points lying in a P E minus F minus 1 plane. So this is the question that we are actually asking, and you see what we had before in just the very first definition that I gave for a secant variety just sets f is basically the same for f equals to 0. But now I want my f to be whatever. So in this case, for example, I have that e is equal to 3 and f is equal to 1, right? Because I have 3 points that lie in a p e minus f minus 1 plane, right? And if e is equal to 3 and f is equal to 1, then I'm going to get 1 there. So that's exactly what I need. And in this case, for the quadrisecant line, I have the same situation. I have, I have e equals to 4, f equals to 2. And so I have 4 points lying in a p1 plane, so in a line. So again, 4 minus 2 minus 1 is equal to 1. So this is now how I'm going to do this. And so you can see now that I'm not considering just the case that I had before. I'm considering slightly more possibilities. I give myself a bit more parameters that I can look at. And of course, I need to impose that 0 is at least f, and it's strictly less than e. So that is also important. Okay. So now to answer the question of when do we actually expect such a curve to contain e points lying in a PE minus f minus 1 plane, I actually want to construct, so to answer this question, I need to construct a moduli space. Let's say now it's VE, but that's actually, I also care about the parameter f somehow, so I need to add it to my notation for the secant. For the E secant E minus f minus 1 planes. All right. So this is what we should do right now. And of course, you see, when I first introduced these secant varieties on the previous page, you could imagine, of course, that, well, okay, I have some planes in projective space. Maybe I could try to do this using some Grassmannians and so on. And you would be right. This is exactly the way you could do this. But I actually want to take advantage here of the intrinsic geometry of the curve. So I would like to take a slightly different path. And this is what I'm going to do now. So I'm going to use this sort of Brunetta kind of approach to things. And I don't want to see the curve as embedded in projective space, but I want to see it as an abstract curve with an embedding given by a line bundle with the correct parameters. So just to write this down, I have, if I say that I have a smooth curve in PR of degree D and genus G, then this is equivalent to saying that I have a smooth curve of genus G, and on top of it, I have a line bundle L of degree D. And I'm going to now basically restrict myself to the case where these linear systems that I'm using are complete. So I'm just going to say that this is equal to R plus 1. And then to make the connection to this picture here is how the, if you want, how the embedding relates to this line bundle. Actually, this line bundle is nothing but pullback of the hyperplane bundle in my projective space. Okay, very good. So now what is, how am I going to write my secant planes in these, in this language? Well, let's see. I'm going to say now that the E secant E minus f minus 1 plane is the same as an effective divisor on my curve. So P1 up to PE, these points can also be, they don't have to necessarily be distinct. So I'm going to write this as belonging to the symmetric product of the curve. So CE is the ETH symmetric product of the curve. So this is C times C, E times, and quotient by the action of the symmetric group, right? I don't care about the order. And now I claim that this E secant, or I'm telling you that this E secant E minus F minus 1 plane is the same as a divisor in the symmetric product with the following property, namely that this dimension here is at least R plus 1 minus E plus F. So actually what this means geometrically is that this divisor here that I had of degree E imposes at most E minus F conditions on my linear system. So this is the E minus F conditions that are being imposed. And basically, this is how this happens here. I have the sections that vanish at those points. And of course, this guy is R plus 1. I impose at most E minus F conditions. Then this is what is going to come out when I do the arithmetic. Okay, so this is what it is. And this is actually a very convenient condition that I can describe my secant planes by, because now I can describe actually this parameter space that I'm interested in. I can cut it out from the symmetric product through via the degeneracy locus construction. So the idea is to cut out now the space of E secant E minus F minus 1 planes to the curve embedded by this line bundle L. So this is why this L here comes out. I want to cut this out of the symmetric product in the following way. So the way this works is I consider the following map. I take the restriction, call it phi, and I take the restriction of this guy to some divisor of degree E. Okay. And so now you see that, okay, I'm going to foreshadow what I'm going to say by writing things like this. And I'm going to say the following, that such a divisor P1 up to PE belongs to this parameter space of E secant E minus F minus 1 planes to a curve C and line bundle with line bundle L, if and only if, yeah, the condition that we just had is satisfied. So if this is satisfied, but you see now I have this linear map here, and now I can just use some linear algebra, and I'm going to notice that this guy is nothing but the kernel of phi, right? Because phi evaluates, right? You restrict sections from here to here. And of course, if my sections vanish, then they will go directly to 0 here. So that's perfect. Very good. And so from linear algebra, of course, this is just going to be this guy minus this guy. And so therefore, the condition that P1 plus up to PE belongs to my secant variety if and only if the rank of phi is less or equal to E minus F. And that is super nice, because this means that now I can set up my degeneracy locus construction of my moduli space. And I can say now that E minus FL is the locus where a certain bundle map that I'm going to explain in a second drops rank. So this guy has rank less or equal to E minus F. So what is this bundle? Well, look here. Here, everything is done just over 1 point, right? But if I consider this to live, if I just consider the whole symmetric product, CE, then of course this guy here is just going to be the fiber of a trivial bundle with this fiber, right? So this is a trivial bundle E. While here, I'm going to have a bundle with these funny fibers here. And this is a certain kind of bundle that is called the tautological bundle of a given bundle. It's a vector bundle of rank E in this case, because this guy has dimension E. And I can construct it rigorously, but I don't want to. I just want to say that basically this map here is the global version on top of the symmetric product of this map that we just constructed here. So therefore, this condition that the bundle map, so like the global version of this guy, if this map here has rank E less than E minus F, then the locus where this happens inside the symmetric product is exactly the locus i.e. that I'm looking for. So the secant variety parameterizing these secant planes. All right. So this is how you construct it. And because of this construction, you also have, you can also conclude, there's a theorem that tells you that if you have a degeneracy locus constructed in this way, then if it's not empty, then you have an expected dimension for it. So if it's not empty, then you know that the dimension of a space constructed in this way is greater or equal than some formula, which in the case that we are considering, the formula gives you this result. So you can see all the parameters that I have used so far are appear E, F, and R. However, not the degree or the genus of the curve, but anyway. And so now this is when you can start doing some enumerative geometry, because you see, if this guy is equal to 0, then it means that my secant variety could in principle be finite dimensional. I'm not quite sure yet, because you see, this is all a bound. I'm not quite sure what the geometry looks like, but in principle, if I can show those things, and if I know that this guy is equal to 0, then I can begin counting secant planes to a variety, right? Because each point here, each point in this guy corresponds to a secant plane to my variety, to my curve. And so indeed, people have done that. So there's been a lot of work from a long time ago and up to quite recently. So McDonald has computed, for example, when this guy is equal to 0, he has given a really complicated but really good formula that gives you the numbers that you want. But it is unfortunately sometimes a bit hard to tell just using the formula whether, for example, when this guy is greater or equal to, when this guy is greater or equal to 0, it's a bit hard to tell if actually the space is non-empty, because the formula doesn't have kind of the nice positivity properties that you need. So then you need to work a little bit harder, for example, to tell this, or for example, to know if when this guy is equal to 0, is this really a finite set, finite discrete set, and so on and so forth. So there's been a lot of work by various people. I apologize if I'm forgetting anyone, but anyway, there's been Coppens and Martin, there's been Cottrell on his own, and also together with He and Zhang, and also Farkas, have studied the dimension theory of these guys here, of the secant varieties, and it's pretty, the conclusion is that things are pretty good. We are in pretty good shape. So for example, we know now that if my variety is not empty, then it is also of expected dimension for a general curve equipped with a general line bundle. Also, we know that if this guy is greater or equal to 0 plus some numerical conditions, so here maybe things can be still improved, then I know that this guy is also non-empty for every C and every line bundle on it, and so on. So this means that the computations that McDonald did are actually valid, if you want. And of course, this is where the generations come in. So a lot of these proofs for expected dimension and so on, they the generations to nodal curves are really are very quite suitable to this kind of endeavor. And I actually want to show you a related but slightly different kind of question that you can ask about secant varieties. And also where the generations of similar kinds to the ones used to prove the results just before are very useful. So another interesting question that you can ask, again in a very enumerative setting, is, for example, I would like to count the double points of a curve of pi degree d1, d2 that lives on a quadric. And so just to recall that the pi degree d1, d2, it means that my quadric here, my curve here intersects the two rulings of the quadric, the red ones or the blue ones, in d1, respectively, d2 points. So this is what this means. And of course, I mean, we already know this. This is a very classical question. We already know the answer to this question. We know by the adjunction formula that this guy is going to have exactly so many nodes, where G is the geometric genus of the curve. But what's really cool is that I can actually reinterpret this kind of question using secant varieties. So it turns out, and I'll explain to you in a second why it's true, that you can either use to get this number, you can either use the adjunction formula, or you can count the elements of a certain intersection of secant varieties on a curve C. And what are these secant varieties? They are the secant varieties V1, 2, so they are cut out the symmetric product of two points. And they are different. And so basically I need to consider two distinct pencils, and L1 and L2 on C. And just a quick note, pencil means that this guy is equal to 1, 2. Okay, so to reiterate, what I'm saying is that it's the same thing to count nodes on this curve in my quadric surface, or to count the elements of this intersection. And first of all, note that this actually makes sense, because if you do the computation, if you use the expected dimension of this guy, you'll see that it's equal to 1, and this expected dimension is also equal to 1. So of course, if you intersect two guys of dimension 1 inside something of dimension 2, and you hope for the best that the intersection is transverse and so on, that you expect that you'll have a finite number of points in the intersection. So at least the problem is well set up. And now let me show you kind of why this also should make sense. So just as an intuitive explanation, you see each of these pencils will give you a map from the curve to the projective line. So this is the map from L1, and this is the map from L2. And the condition that a divisor P1 plus P2 belongs to this secant variety of this pencil is equivalent to this. So this is just a definition of the secant variety. Of the secant variety. But this means that this is just, this is effective. So this means that this P1, P2 belongs to my pencil. So this means in particular that that these 2 points, P1 and P2, belong to the same fiber above a certain point on my P1. And the same story, of course, for the second pencil L2. And so, of course, if you now combine these two things, because I'm mapping not to P1, I'm mapping to P1 cross P1. If you combine these two things together, you will basically see, so I hope you can believe me, that basically that you will get a node together where these 2 points are the same. And so more generally, you can set up this question in a much more general way. And this is something that I have looked at a couple of years ago, and you can show much more complicated intersections like this behave well, because you saw just now the intersection has to be good because the numbers that we got out are the correct ones. So there's no problem there, everything is fine. But here, if you take slightly more complicated intersections of different kinds of secant varieties on a curve corresponding to two different kinds of line bundles, you might not know, right? You don't know to begin with what you're going to get. So my result was that these guys, this intersection here is non-empty, is empty exactly when you expect it to be by dimensional consideration. So this means that the dimension of this guy plus the dimension of this guy is less than something that's an inequality that I don't really want to write down. And that's very nice. So for two reasons. One reason is a geometric reason, because of course this doesn't look like much, but you can interpret this as some kind of generalization of some tag nodes. So for example, you know that if some parameters are in a certain way, so this is what when it is expected to be is supposed to mean. So when some parameters are in a certain way, then you can expect that your curve doesn't have some kind of funny singularities. So that's nice. When you send it, when you map it to using these two linear series here. So this is one nice feature, but another nice feature is that it gives you kind of the proof kind of gives you a nice recipe to deal with a certain kind of setup that I'm going to explain to you now. So the point is that this kind of statement that an intersection of certain secant varieties is empty is equivalent to a system of equations. And what I mean by system of equations, maybe I should put it in brackets, in quotes, is that, for example, the line bundle corresponding to two divisors on the curve, D and E, and the divisor, the line bundle corresponding to the divisor 2D plus E on my curve. So if these line bundles have to be equal to something else, so have to have a fixed degree and a fixed dimension of their space of section. So if this is the system of equation, and if this system of equations does not have a solution, then this statement also holds. So to recapitulate, this intersection here is empty if and only if a system of equations of this type has no solution, right? And here, basically what I'm trying to say is that I'm fixing the degree and the dimension of the space of section of these two L and L prime. And this is the kind of thing that actually pops up every now and then. So it's nice to have an idea of how to deal with these kinds of questions. And this is where the generations. So, for example, you assume towards a contradiction that this guy actually does have a solution. So assume that star has a solution for a general curve in MG. Then there is a really nice result by Farkas that tells you that then the same has to hold, then the same holds for a flat curve. That I'm going to draw. So this is my flat curve. It consists of a rational spine, R. So this R is a rational curve, together with some elliptic tails. So these are all elliptic tails. So if the system has a solution for a general curve, then this very nice theorem by Farkas tells you that this has to also be true for this guy. And not just that, but in a certain configuration such that the points in the supports of D and E either coalesce into a single point on the rational spine, or they live on a subcurve y. So the subcurve y would be maybe something like this, right? Of this flat curve with a certain property that its arithmetic genus is at most the degree of d plus n. So you see, this is quite restrictive, and this is really cool because once you have something like this, then you can start playing around with various combinations, and you can start getting all sorts of nice contradictions using the Plücker formula and so on. So this is a very powerful result. And incidentally, it was also used in the previous results about the actual expected dimension of the secant variety, VEE minus F, so not just in this kind of intersection of secant varieties context. So that's very nice. And then, of course, you can ask, okay, but what does it mean for a divisor to have a certain degree and a certain dimension of the space of sections on a nodal curve? We don't know that, but we actually do know, because we have a very powerful setup of limit linear series of Eisenbud and Harris that we can use. So that actually gives you all the technical stuff that you need to be able to compute this. But it's quite technical, so I don't want to go into those details. I also want to say that it's actually super fun to construct this kind of degeneracy loci, not just for a curve like we have done so far. You can actually do this kind of argument also to construct it for a family of curves, and not just a family of smooth curves, but also family of nodal curves of compact type. So this limit linear series methods and tools are really quite powerful, so they allow you to do even that. And that's also quite nice if you want to construct, if you want the space of all possible secant varieties on top of a family of curves. So that's also quite nice. Okay, so this is what I would like to say about the generation. So this is kind of how you go about checking whether what you know, whether the space that you're trying to understand is, has the correct dimension or has intersection properties that you want, and so on and so forth. And whether ultimately, for example, the formulas that MacDonald computed in the case when the secant variety has dimension 0 are correct. And this brings me actually to the last things that I would like to say in this talk about the tools that you might need in order to compute these kinds of numbers. So what I would like to say first and foremost, okay, I just reminded you what I'm trying to do, that if the dimension or the expected dimension is 0, then we can count. And actually what you do is you compute an integral, or if you want, you compute the degree of the cohomology class of the space that you are interested in this case of the secant variety. Okay, and how do you do that? Well, another good thing about our construction of the secant variety as a degeneracy locus is that you kind of get for free its fundamental class. So there is a formula by Porches that tells you that this class is going to be given. So this class here is going to be given by this ugly looking determinant here. And notice that here, these are all Chern classes. So all these C's indicate Chern classes of certain degrees. And you see here the main character. So the bundle with respect to which we compute these things is this tautological bundle that we introduced earlier, and that was used in the definition in the construction of the secant variety. Okay, so now MacDonald computed this and came up with a really impressive formula. But the thing is, it's as I said before, it's a bit unwieldy. So we would like to maybe understand a little bit the structure of this formula. So now a really nice tool that I learned recently is this very cool result by Ellingsrud, Kirch, and Len from 2000, and which was later generalized by Rendemont. That tells you the following thing: if I want to compute the integral or the degree of a polynomial in Chern classes of such a tautological bundle, then I'm in luck because this guy is going to be a polynomial in the first Chern class of L and the first Chern class of the tangent bundle of the curve. And that's really awesome because this means that, I mean, I can use this on my in my case as well, because you see this guy here is a determinant, right? This is definitely a polynomial in the Chern classes. So definitely this guy fits this description, and therefore I can conclude that this integral field depends only on the degree of the line bundle, right? This is what this is D, and on the genus of the curve, which also comes from here, because this is, depending on your taste, 1 minus g, 2 minus 2g. Okay, so this is a very nice this is a very nice thing that you might want to use to try to understand these kind of formulas and to try to find some structure in these calculations. And now, of course, this is not, in some sense, it's not surprising, because if you stare at McDonald's formula, of course, you will also notice that things are going to be polynomials in D and G, but I think it's very reassuring that actually this result holds anyway. So now, for example, sort of nice reformulations of McDonald's formula already exist. We have, for example, when the parameters is f is equal to 1, we have some really nice formula that were found independently by Cotterill and Lepars around 2007. So they showed, for example, they found this really cool generating function for the for these classes here. And you see, of course, just as I said, you see immediately that the D and G minus 1 are the only things that show up. But now the thing is that it turns out that it's really quite difficult to do this for other choices of F. And this is something that I would like to understand a little bit better. Because it seems that, at least from the point of view of the Ellingswood-Götzsche-Lenn result, f equals to 1 is a bit special. And it's a bit special because in that case, the integral, so the class under the integral sign, is a special kind of class. It's actually a top Segre class. And when it's a top Segre class, then another result by Ellingswood-Götzsche-Lenn from the same paper tell you that actually then that kind of generating function will have a very nice shape. It will be the exponential of some generating function and of some power series. Sorry. So that's very nice, and somehow you keep getting these hints that f equals to 1 is a special case. As we saw also here, you can get like some really nice results there, but somehow I don't quite understand why that is the case. So I would like to understand what happens with other choices of f. And so recently I tried to, okay, let's try to use just purely this result of Ellingswood-Götzsche-Lenn to try to find this kind of formulas for this. So I didn't even try the generating function, just purely I would like to find these guys here. And okay, so how do we do this? How do we take advantage? Well, the point is that because these guys here are polynomials in D and G, then it doesn't matter what I stick inside here, what curve and what line bundle I put inside it, as long as they have the correct parameters of degree and of genus. So I might as well take some particularly convenient choice. So for example, I might as well take the curve to be the projective line, and I might as well take the line bundle to just be this tautological line bundle on P1 of degree D, and just do an induction on this on these guys. And because why I'm choosing this because you see, I know immediately what the symmetric product of the projective line is. It's just PE, the ETH symmetric product of the projective line is just PE. And also I know how to compute the Chern classes of the tautological version of this of this bundle here. I also know that it's this, where H is the hyperplane class. So that's very good news, because then I can just essentially do my induction by constructing curves by taking disjoint unions. So if I consider the curve C1 to be the disjoint union of P1 and some other curve C2, then using the additivity of the other characteristic with respect to these kind of things, then I conclude that the genus of C2 is nothing but the genus of C1 plus 1. So very good. I can go up and down in genus. And also, if I have a line bundle on this curve C1, then the degree of this guy is also going to split like this. So that's also very good news. I can also go up and down in degree. I also need to, of course, understand what the symmetric product of this kind of thing looks like, but that's also not too difficult to see. This is also disjoint union of these kinds of products here. And I also need to understand yes. I also need to understand what the tautological version of L1 is going to be, especially restricted to all of these components here. But that is also not too hard to see. And this is, I'm just going to, to tell you what this is. So for each P1 and for each of these components, I have projections P1 and P2 to P1 and C2 M, and on each of these guys, I have this and this. That's an M here. Sorry, it's a bit small. So on each of these guys, I have this, and L, of course, is just the restriction here, and L2 is just a restriction of L1 to C2. So basically what I'm trying to say, it's a lot of notation, I know, but what I'm trying to say is that if the way you construct the induction is you start with this particularly good case that you can compute quite easily, and you go up and down degree and genus using disjoint unions, using what we know about disjoint unions, what they do to the degree and the genus, and using what we know about what happens to the symmetric product and to the tautological bundle. So that's very nice. So for example, if you do this, you just set up a recursion, you turn the crank, you put it in a computer, whatever, and you can recover nice formulas. For example, you can recover the formula that if C is of degree D and in P3, then it has so and so many 4 secant lines. And this kind of polynomial, so these polynomials in the degree and the genus that I've been mentioning all this time, these are what these universal polynomials are. So this is the nice thing about it. But of course, as I said, I still lack somehow a conceptual understanding of what happens when, you know, when I go from f2 equals to 1 to f equals to 2, why does stuff blow up? And so I would like to just tell you what I would like to try to use in order to explain this. So this is very much work in progress. I'm just very excited about it, so I will share it with you. So what is very nice, there was Groznovsky and Nakajima independently in 97 and also work by Len in 99. They understood the following thing. So this was done, basically everything that I've said so far, that I've said about curves, you can pretty much also say about surfaces, about smooth projective surfaces. Of course, you have to be a bit careful because now you have to replace the symmetric product with the Hilbert scheme of points of a surface, but that's okay. And so what it was noticed was that you can construct some very interesting linear maps between, so QNs for each n in Z from the cohomology of, say, the projective surface to this endomorphism ring here. So this is, as you can see, this is now the cohomology of the Hilbert scheme. And not only that, but they also satisfy certain commutation relations that looks like this. This is the chronicle delta symbol. And basically, you can use this to show that these guys actually induce you a representation of the Heisenberg algebra on these on this space here. And then once you do that, okay, physicists would say that, of course, that's true. But once you do that, you can also repackage all of these QNs into a Virasoro algebra. So you can take products of them and so on until you get a Lie algebra that has a certain commutation relation. And by the way, also is very important in conformal field theories. Right, so that basically what I'm saying is that these things have a lot of structure here. And so another thing you can do is you could rewrite everything that I've said so far in terms of these operators Q. Instead of, you can rewrite, for example, all the Chern classes and everything can be rewritten in terms of these operators Q. And so my question is, does this help? So then basically the open question for me right now is, could one use these things to understand a little bit more the structure of the formulas that I have seen so far? Would it help, for example, to find out that these secant varieties give you some interesting subalgebra in these situations and so on? So anyway, I would like to stop here and leave you with this open question of mine. And yeah, thank you very much for your attention.
Thank you, Mara. Thanks, Mara, for beautiful talk. Thank you. And in Zoom, like this. Okay, thank you very much. Questions, please. I had question, Mara, but you answered it partially in the very end of your talk. So what about high dimensional things? Yeah.
Yeah, so that's the thing. Things get very hard because, of course, then the Hilbert scheme of points is also not smooth anymore. And for example, in these in this setup here, you kind of need that to make it work. So for higher dimensional things, this is it's not like you don't know anything. So for example, when I mentioned here the work of, sorry, I'm getting there. When I mentioned here the work of Renemo, so these Ellingsrud-Götzsche-Lenn, they proved this result about the universal polynomials. So this was proved up to surfaces, but then he did this also for like any varieties of any dimension. So for example, there is hope in that way, but whether, yeah, I don't know. It seems it gets incredibly complicated once once you leave the Hilbert scheme of points of a surface. So this smooth kind of context. Yeah.
Very good. Thank you. And I have some question. It's not very precise, but in general, this is a bit far away from me. But for example, I met recently some special birational, several birational maps I actually learned from Sasha Kuznetsov that relates to seconds. Just if I give you one example, maybe it rings a bell. Maybe you have, is it okay? Mm-hmm. So for example, if you have P4 and you have a Veronese surface in P4, projected one,
yes.
not projected from general point in P5, yeah. Then it has a lot of 3 seconds. Yeah, mm-hmm. And 3 seconds span P4. So if you blow up this Veronese surface, all these 3 seconds split, and you have a P1 bundle of a famous Fana threefold called degree 5 index 2. So you have very nice birational construction that helps to understand the geometry of the threefold a lot. So what I want to say that sometimes the second variety, or special seconds that related to some nice maps or something in birational geometry. Did you meet something like this? Some nice birational constructions related to?
Yeah, that's a very good question. So I would say yes, but I don't want to embarrass myself because I'm not sure I can be particularly precise. But
it's open-ended.
Yeah, that sounds quite familiar with respect to other things that I've seen. Yes, but I'm not quite sure how to put it in like a general.
No worries.
Context. But yeah, it's true. They appear like whenever you do a projection, you can.
Okay.
Okay. Yeah.
Yeah. Thank you. Thanks. Good. Okay, great talk. So let's ask more people if someone have questions. If you have a question to Mara, please ask. No. Okay. Okay. I thought it's a question to talk. Thank you. Okay.
May I ask a question?
Yeah, definitely, Michael. Yeah. Yeah.
Or maybe more, it's a comment because I'm working over finite fields, and you've mentioned many applications, and I just want to say that also over finite fields there's a huge number of applications of secant varieties, but also of spaces disjoint from secant varieties. And these give you several types of error correcting codes, for example.
Cool.
They're also having applications in cryptography using semi-fields, which are a type of non-associative division algebras. So there's a whole area there that I'm not sure, of course, if your techniques are applicable there, but there are definitely a lot of applications also over finite fields. You've mentioned the tensor decomposition.
Yes.
Do you know if your techniques can help in maybe for certain classes of tensor to develop some kind of decomposition algorithm?
Yeah, so I'm not, I think this is not necessarily the right context. So the ones that I've seen, these applications to these tensor decompositions, they are not so much this kind of like curve, sequence to curves and so on, that they tend to be more along the lines of what Vanya was saying. So it's more along the lines of sequence to Veronese or something like that. And there this is like high dimensional stuff and it's hard. Yeah.
Yes, I should have rephrased my question. Instead of saying tensor decomposition, I mean, you can define the rank of, with respect to any kind of variety. So it does not need to be the tensor rank, but just in general. Do your methods allow you to develop some kind of algorithm to determine the rank of a point, let's say, in your space?
Yeah, I would have to think about that. So I would say I don't know. I'm not sure if that's true.
Good answer.
Yeah. I have not thought about that.
Good question, Michael. Thank you.
But it's yeah, it's really interesting. I also didn't know that this was something you know, that they showed up also in cryptography, and yeah, I had no idea.
Thank you.
I have a question.
Yeah, please.
Not mathematically related. You said that it's got applications in signal processing. I was wondering if you could elaborate a little on that.
Yeah, it was this tensor decomposition part. So these when I don't know the details, let's say, from the signal processing point of view. What I know is that in that kind of field, eventually what the mathematical question that you get is the decomposition, is such a tensor decomposition question. So maybe someone else knows more precisely the actual background in the signal processing, but I know that basically questions like that end up being, if you want, conjectures related to, conjectures about the, you know, vanishing ideals of a secant variety. But I don't know how you get from the signal process to the tensor decomposition. That is something I don't know.
Awesome. Thanks.
Thank you, Mara. Any other questions to Mara? Mara, I have a non-mathematical question. Did I pronounce your name correctly? Ungureanu.
Yeah, it was perfect, actually.
I have actually a friend with the same last name.
Yeah,
from Moldova. Yeah.
It was spot on, yes.
Yeah. Okay, if we don't have any more questions, let's thank Mara again. Thank you.
Thank you very much.
Great talk. Okay, I'll upload the recording today in the evening, a bit later.
All right. Thank you very much.
Thank you, Mara. Hope to see you
See
one
you
day,
around.
maybe in Edinburgh, maybe in Germany. Bye.
Thank you. Bye-bye.
Bye-bye.